So it's a real pleasure and an honor to introduce the next speaker here at End Summer Camp. He is a PhD at Politecnico di Milano and an associate professor now. His research is malware analysis and is on the board of Black Hat, right? And he is Stefano Zanero. You probably know him already. So please welcome him. And here we are.
Thank you. So in the spirit of having at least one English speaker in the audience, I will speak in English. If you don't understand me, which is perfectly understandable, just raise your hand and I will repeat myself in Italian. So my name is Stefano. Yeah, like Pila. Yeah, right. Sure, you're just the one. So okay, so I have way too many friends and way too many enemies in this room, and it's always difficult to tell which is which. So my name is Stefano. I work at Politecnico di Milano, and this is actually what I'm going to present is actually joint work with my equipe of colleagues and friends that I will list at the end of the talk. We are working on different things. One of the things we are working on is how to make sense of 1 million samples per day, how to make sense of a lot of malware that is getting thrown at us. So this is in the framework of an activity that is called threat intelligence. Threat intelligence is not new. In fact, it has been winning or losing battles since 500 years before Christ. This is a famous quote from the Ping Fa, The Art of War by Master Sun Tzu, which has written it about 500 years before Christ. And he said that if you know the enemy and if you know yourself, you're going to win every battle. Then, of course, this is one of the most often quoted and most and least often applied quotes in human history. But basically, knowing our enemy is always important for fighting the cybersecurity battle. And here we have a significant issue, which is the evolution of the threat, or the evolution of malware. So if you have been in security long enough, and know that some of you have been in security long enough, in particular Pila has been in security for a very long time, is kind of the grandfather of all of us. So if you've been in security for long enough, you will remember that in the 80s and 90s, most of the malware that we had to deal with was self-replicating malware. It was malware that was self-similar by construction. It created a lot of copies of itself. So it made almost sense, the idea of just looking at each of these samples and understanding what they were doing and kind of creating a catalog of malware, which is what antiviruses basically are, catalogs of malware. There's also another significant feature of the malware written in the 80s and the 90s, that most of the malware that was written in those ages, so the statute of limitations in Italy has expired. Most of the malware that we wrote in those times was basically aimed at demonstrating skill. We didn't really want malware to be destructive. There were some destructive samples, of course. There's always been destructive things. But most of the malware back then was destructive only by chance, because somebody made a mistake. This has changed over the years, and in particular, this has changed a lot between the 2000 and 2004. You will remember the ages of the worms. There were this enormously diffusive, explosive malware that would propagate and create damage just because of how fast they were propagating. And in 2004, we were all basically betting that malware that was propagating as worms would become worse and worse, that the internet would become wormier and wormier. I even have, I'm sorry that I wasn't able to find it for today, but I even have a T-shirt which was by iDefense a few years back. That on the back of the T-shirt, like it had the dates of the worms, like the dates of concerts of rock bands, right? It was made in the same way. So we were all betting on the next one, but the next one then never appeared. From 2005 till today, what we have seen is the malware authors shift focus to actually monetizing through diffusive stealth malware that is not actually a clone of itself. And this change has been fueled by the growth of the underground economy, so-called crime as a service, where people actually buy code for doing malicious things instead of writing it themselves. So there's criminal rings that are running different portions of the malware food chain. But what happened in there, in that shift, is that we shifted from malware that was always the same, many copies of the same thing, to malware that was basically always different. Right now, we get between 500,000 and 1 million new different binary samples per day. In all that lot of malware, which is mostly the same thing really, but just slightly different, in all that malware, there's also other people that are hiding. So for instance, from 2010 on, we have been witness to an enormous increase in what we call state-sponsored attacks. In the middle of all that shit that is thrown at us over time, all that 500,000 new malware, there's 1, 2, 3 per month or per year that are actually more interesting. And what we need to do is figure out a way to filter out all of those 500,000 that we don't care about, to sift out that 1, 2, 10 that carry information. There's another issue that we need to deal with. And the issue is the issue of so-called attribution, which doesn't mean saying, oh, this malware has been written by X. Not really. It means this malware comes from that area, that family, that threat actor. And this is difficult. It's always been difficult. The problem is that right now, instead of it being difficult in the sense that we wanted to know which hacker group was responsible for that specific cool piece of malware that we were looking at, and most hacker groups in the 90s would actually embed in the code of the malware their own signature to just let you know, hey, this is cool, I did it. Right now, we have the issue of actually trying to understand who's done it, because sooner or later, the answer to that specific entity doing it may be a well-placed missile. So we need a way to figure out very well what malware does, which malware is interesting, and when we find the malware that is interesting, to find out who's his dad or mom. So the issue that we are dealing with is that we have a lot of code and we have a few analysts. And do not mistake me, I'm a professor, I'm training people, and I'd love to train as many analysts as I can, but we will never be able to train enough analysts to analyze millions of samples per day by hand. These analysts we need more analysts, we need more people skilled at that, but we need a better way to analyze malware than looking at its code. In order to understand what it does, in order to understand if it's new, in order to understand where it comes from. So the people that are already aware of malware analysis techniques, and I see quite a few in the room, will excuse me if I go back to the basics, but for anybody that has never done anything in the malware analysis area, there's 2 ways that we can analyze malware. And they're not like the wrong and the right way. They are just 2 complementary ways. So one way is doing static analysis, taking it apart, looking at the code, disassembling it, reassembling it, trying to understand what it does, what the specific functionalities are by looking at the code. That's what we used to do with malware in the 80s and 90s. Look at it by hand. It works perfectly. But it takes a lot of time. It takes a lot of skill. So, which is the difficult to extract semantics line over there. There's also another issue, which is obfuscation. Most malware nowadays is obfuscated or packed, which means that it's not easy to extract its meaning. So for most malware, we actually employ also a dynamic approach, which means basically you create a sandbox, a virtual machine which has been cut off from the rest of the internet, and throw it in and so see what it does. At very least, let it unpack itself. Let it uncompress itself so that you can look at its code. And then look at what it does. Look at its behavior. And this is actually easy because it makes it easy to see behaviors. You can actually figure out what the malware is doing in a very automated way. That's what basically most malware analysis systems in the world do as a first basic measure. But this is a major issue. When you run the malware, you only see the behavior that the malware is showing to you. So you have the issue of dormant code, of code that has not been executed during that specific execution of malware. So how do you solve these symmetric weaknesses of these two approaches? You usually use them together. So the research that we are doing is in hybrid analysis techniques where you mix dynamic and static analysis in order to try to figure out more about the sample. And one thing that we actually found is that why is there so much malware? Answer: because people reuse code. They cannot write 500,000 samples per day all from scratch. They're just reusing code over and over. So let's turn the tables. Let's use this code reuse against the malware authors as much as we can. So I will present 3 different things that we did based on this concept, just to try to let you understand how powerful it is and how it can be applied. So the first is a prototype that we called Reanimator. This is actually reasonably old research because this was presented in 2010. It's kind of the basic idea behind everything, so I thought to start from here. So in Reanimator, what we do is this. We run a sample into a sandbox. This sample shows some behaviors. These behaviors are sometimes interesting. For instance, I see the sample running an attack, an exploit that I have not observed before. So this behavior is interesting for me. I can track that behavior to a specific model of the underlying code that is resilient to recompilation and that tracks back that code as much as possible to the source. Then, with that model, I can go through my set of samples that I have collected over the years, and I can see if there is another sample that implements the same capability. And it has not shown it to me because reasons, whatever. So basically, well, identifying the behavior is simple. You run the malware instrumented sandbox. You used to be able to run it into Anubis. I'm still able to run it into Anubis, but you may not be able to because they have pulled Anubis from open access. But you can do this with any sandbox you like. We did it with Anubis. It's not necessarily tied to that. The only thing that you need is to be able to basically arrive to a set of API calls that the malware has executed that implement a certain behavior. And this behavior can be something as generic as sending spam or something as specific at attempting a specific exploit against something. So once you have extracted that behavior from the malware, you can go and try to match, and this is actually the difficult part. The rest of this is actually just an exercise. But the difficult part is how do you map that to code, to binary code, in such a way that you can basically go and match that binary code across a collection and see if there are other malware that have implemented the same behavior starting from the same source code. So here the problem is that you want to basically include all of the code that has implemented the behavior, but you don't want to include code that is supporting features or is not specific to that behavior. So we have a process for this, and the process is this. We start from the API calls, so from the slice of API calls. We create an empty slice, and we include in that slice all of the instructions that either prepare the inputs for the calls, so basically we follow data dependencies backwards, and we process the output of the calls, so follow the data flow forward. Here we make a major assumption because, of course, any I see Meredith agitating in the back. So any computer scientist that has dealt with this problem knows that there are a series of challenges in this. One of the challenges is, of course, counterflow dependencies. But the cool thing is that most malware does not really have that significant set of counterflow dependencies. So we kind of take the shortcut and and simplify that. So at this point, we have an issue, which is that the slice is not precise. It includes also all sorts of supporting codes, general purpose, utility functions, and so on and so forth. And also, actually, if you go backward slicing and you do it very well, at some point you may basically hit the initialization and the unpacking routines. And at that point, you're screwed because you basically matched all the code of the malware. So we basically try to filter this. And the idea of filtering is that we use exclusive, we basically look at exclusive instructions, which means we have multiple runs of the malware. The malware sometimes exhibits the behavior, sometimes it doesn't. So if an instruction has been patched, both when the malware has exhibited the behavior and when the malware has not exhibited the behavior, it's probably an utility function. If a function manipulates tainted data every time it's executed, then it's specific to that malicious behavior. Otherwise, it's an utility. It may be an utility function. We can also, in theory, we could use whitelists, so we could basically map like libraries and whitelist code. But this is not really necessary, because if you apply these two techniques, you are basically discarding every type of library. At this point, the slice that you're left with is obviously not complete because you have thrown away a lot of stuff. So what you do is you start from those instructions and you basically complete the basic blocks around it. And you end up with a sub-portion of the control flow graph of the malware that then you need to somehow match to other samples in a way that is resilient to recompilation, but not too lax. In order to do this, there is actually a technique that has been used over and over in the years, which works reasonably well. It's been developed by Chris Krugel a few years back for matching polymorphic malware. And the technique is based on the idea of coloring the control flow graph according to some instruction classes. Basically, you can divide x86 instructions into buckets where in order to substitute one of the functions with equivalence, you really need one of the other functions in that bucket. So if you color the control flow graphs based on those instruction classes, it turns out that if you go and match all of the subgraphs of a certain size between two different control flow graphs, if there are matches, those two control flow graphs, those two executables, are very, very likely, for a high value of very, very likely, to come from the same source code, or to at least include a part of the same source code. So then the question obviously is how much very, very likely they are to be from the same source code, so if this is accurate, and how insightful it is. So for accuracy, of course, you need to have like a ground truth. So we started from a data set of a couple of hundred malware samples that come from University of Michigan, that they have collected malware samples and the relative source code. And so we tested that by basically running our approach on one sample and then matching it against the remaining binaries and seeing where the matches were. Of course, even with source, manually verifying matches, and in particular non-matches, is kind of long. So it's basically years of PhD student time, which is a very precious resource that should not be wasted. So we basically use that trick. We use the MOS, which is a very well-known code plagiarism detector that most professors use to detect students that cheat at exams and copy the same code. We fed MOS to the source code corresponding to the behaviors, matched it against the other sources, and basically we expect our tool to match in cases where MOS returns high similarity scores. So this is kind of the most useless graph that I've ever drawn in my career. So every time I present this graph, I realize that it sucks. So basically the blue bar is the result returned by MOS in a percentage of match against the couple's behavior bot. So basically what we would expect is that Reanimator returns exactly the same levels of match, but it doesn't obviously always happen. So in this graph, the difference here is the most likely things to be false negatives. MOS says these matches, I say this doesn't match. These things here are the most likely ones to be false positives. So MOS says, no, this thing is not the same. And I say, no, this thing is the same. So we, and when I say we, I intend the first author of the paper who is a PhD student, who was a PhD student at the time, manually investigated false positives and negatives and found out that we have a false negative rate. Of course we do. It's a completely unsupervised way of matching things. But it's relatively low. It turned out to be about 1.5% on our data set. So few tens of mismatches, which mostly relates to small genotypes, small pieces of code that are so small that they do not really work well with the idea of creating subgraphs of size X. The cool thing is that we found no false positives, neither here nor by running other tests, nor by, for instance, running a test where we tried to match that code on an enormous code base of a Windows computer. We've installed all of the software that we could think of just to see if this would match somewhere randomly. This is partially robust when recompiling from the same source. It's robust against trying to change compilation options or compiler versions, or by embedding code in different pieces of programs. But for instance, it's not really robust against a completely different compiler, because calling conventions, because different instructions. Actually, this difference is mostly due to the way we extract things than to the approach itself. But still, that's the data, and that's what I'm showing. So I will just accelerate and leave you to go through the whole data set. If you're interested, the paper is called Reanimator. You find it in IEEE Security and Privacy 2010. But basically, you will, if you browse through the paper, you will find that this actually discovers a number of instances where a behavior is implemented in bots and it's not being showed. But this is obvious because bots, of course, are command and control things. If you don't have the commands coming in from the CNC, they will not show a behavior. Then we decided that we wanted to use the same idea to track the malware evolution over time. So once again, for those that are not really really proficient with malware, it's better than water. So most malware nowadays automatically updates. It has an update mechanism, just like the Windows update mechanism, only the difference is that it works. And basically, what we did was we collected a number of malware families that would self-update, collected all of the updates, and tried to understand how they were updated, why they were updated, what they were changing. So the idea is that we have our malware sample, we let it connect to the update server over time, collect all of the variants, perform a binary comparison to see what are the code changes, but also perform a behavioral extraction with the same technique that I showed before, matching the code and the behavior together and try to figure out how these binary changes map or not to behavior changes. So the idea, the question is, do these people change things because they are just patching stuff? Or maybe they are just changing stuff just to screw up with signatures? Or do they actually change things, implement new things? So besides some global results, which actually say that, for instance, there are families that from one day to the next have as much as 12% or 20% of their code added or removed. So with significant changes from one sample to the next. But this is a kind of analysis that you can do very simply by just comparing the binaries. What you can do by using our techniques is that you can break down the changes over the behaviors. So for instance, we know that running a DNS query is such a standard thing that from one sample to the next, the average is that the two code sets are always the same. Nobody changes that. But there is one sample over the month of observation which has a completely different behavior. And then the behavior remains implemented in that completely different way for the subsequent samples. If I'm an analyst, this may be interesting. Out of all those samples, this one and this specific behavior, I may want to look at. Why did they change the way that they resolve DNS? Because it doesn't make a lot of sense. If I have a generator of UDP traffic, and there is one sample where this UDP traffic generator has been changed, why did they change it? Because maybe they changed it because they needed a different set of options for an exploit that they were running. Or maybe they changed it because they patched a bug or a vulnerability of some sort. And I may be interested in looking at that. So the paper is actually much longer than this, and it's been published at AXAC, so you can go and fetch it online. But the insights that we had is that, well, of course there are families that are more actively developed than others. There are younger families and older families. But even in families that are not really actively developed, there are some specific points in time where people deploy a new version of some behaviors. The effort behind this is difficult to actually estimate because we have blocks in assembly, not really line of code. But since, for instance, for Europeans and Italians, Zeus, for non-Europeans, Zeus, we have different, we have also the source code. We estimate that, for instance, for the average day-to-day update of some Zeus variants, we are around the 200 lines of code that have been edited. So every day there's somebody that patches and commits and compiles 200 lines of code. But there are peaks of 9,000 lines of code. This is a significant engineering effort. So there's a significant amount of money and of time of people spent in developing malware. Actually, one of the side effects of this research was this. With Reanimator, we were specifying an interesting behavior, and we were going and tracking it across the data set. And we were doing that manually. This is interesting. Tell me all about it. With this approach, we actually wanted to track the changes across the whole malware. For some of them, we could manually say that this was this specific behavior, as in the tables that I have shown you. But we wanted to do this in general, over all the malware. So we wanted to find a general definition of what could constitute a behavior, a unit of behavior of a malware. And the best definition that we found, you can challenge it, but the best definition that we found is this, that basically a behavior in a malware, in a Windows malware, is a collection of API calls that are connected between each other by exchange of parameters, by tainting, and that are repeated, that happen all over the time. So they don't happen casually just once, but they kind of keep being repeated. So we began thinking about it, and we began thinking, okay, then maybe we can automatically extract from a large body of malware the description of behaviors, of common malware behaviors. And take care, not necessarily malicious behaviors. Common malware behaviors. They could be resolving DNS, but they are common behavior found in malware. And this is actually a game changer because you can pick up this data set of malware, and instead of analyzing the single samples, you can go and tell the machine, okay, generate me the description of the behaviors that are in here. And then you can look at the behaviors and give a name to the specific behaviors if you recognize them. And once you tag the behavior, that name, that tag, is going to backpropagate throughout the database to all of the samples implementing that. So this is the intuition to go through data flow analysis. I'm skipping over slides because otherwise I will go over time. But basically, we are doing this by doing a major clustering analysis where what we cluster is not malware. We are not clustering malware, for instance, to try to find the families. We are clustering pieces of malware in order to find common behaviors, which is kind of the thing that we had to explain 4 or 5 different times at 4 or 5 different sets of reviewers before this paper was accepted, because it was actually kind of difficult to get this through. So we were there with our kind of models automatically extracted from malware, and we were thinking, okay, can we do something more? Like automatically tagging this not with a description, that's for humans, but with some tags, some descriptors, and we, yeah, type. That's the obvious one. No, something a little more semantic than a type, actually. But yeah, but that's obviously, well, that actually goes back to the connection between APIs. There's a lot of inference on types that I'm skipping, but you may actually be interested in looking at that. So we were saying, okay, so we have a list of APIs, of Windows APIs. How do we extract from a list of Windows APIs a human description of what are they related to? First thought, Windows APIs. What documents Windows APIs? TechNet. Go to TechNet documentation. Try to parse it. Worst idea in the world. I presented this same thing at Blue Hat at Microsoft's internal security conference, and there were like the Windows people in front of me saying, nope, no, you don't want to do that. TechNet sucks. So we went to the second best documentation of Windows API, Stack Overflow. And in Stack Overflow, there's these interesting things that you tag your posts when you post. So if we look at posts related to a set of APIs, and we look at the tags, and we do some semantic filtering on the tags, so we throw away things that are useless, we can extract descriptions. So for instance, this is an automatically extracted behavior, which is basically opening a URL. Don't open this if it's active, because that's a malicious URL. And these are the automatically extracted tag. If you run this through Stack Overflow and you see how the posts that contain these same APIs are tagged. And of course, there are some things that are not really interesting, like Microsoft Foundation classes. But there are some things that describe that pretty well. HTTP, file, internet, file download. So, can we tag automatically the behaviors? No, of course not. But we can give them some tags that are useful for an analyst that has in front of them like 3,000 untagged behavior and they're only interested in HTTP-related ones, to filter out the HTTP-related ones fast. Then one of the things that we were asked by a nice reviewer that rejected our paper was, yeah, but how do you show that this does not only happen because you had your bunch of malware with your families in it? And if you add a new family that you have never seen, this family is probably not going to be covered by your research. Well, we showed that by basically extracting one family at a time from our dataset and showing that they were all covered, because even the families are different, and so the code implementing the behaviors is different. The behaviors themselves are very self-similar when you look at them at the generalized API level. Also, we found that, for instance, by having experts manually describe to us behaviors that they knew some families would display, we had 45 descriptions generated manually by analysts, and the system automatically generated 43 of those. Obviously, this is the ground truth behavior and the automatic behavior. If you look at them at the high API level, it's going to be true. But sometimes what happens here is that since the automatic extraction is automatic, the machine does not understand what is the core component of a set of API calls and what is just an accident. And so here you may have an overspecification, which decreases over time depending on how many families you show to the system. So the conclusions on this are that you can combine dynamic and static analysis in order to tag and analyze dormant code in malware connections, to track the evolution of malware over time, to automatically extract, and also up to a certain point automatically tag behaviors. We are now building this last system that is called Jackdaw so that it can be used in a crowdsourced fashion. So you can use a plugin in IDA to basically analyze the malware that you're looking at, see the components of behaviors, automatically tag them if there is already a specification, or write your own specification and propagate through the data set of malware. And you can do this in a very agnostic way, because since we are not transmitting the code of the sample, but only the recognizing features of those sets of API calls, you are not sharing a sample that you may not be able legally to share with someone else, but only your analysis, and using a crowdsourced analysis of data sets. In the bigger picture, what this can help to do is to characterize adversaries based on the artifacts. Because of course you create a map of behaviors, and then for each behavior you create a set of different implementations. The implementation actually characterizes the author. You can extract actionable intelligence because you can see the new behaviors instead of the new samples, because the new samples are too many. And we hope to provide a community-oriented methodology to improve malware analysis in this way. So with this, I'm done. You can send me feedback. Stefano.zanero@polyme.it is my email, or you can tweet at me. I like it. Well, depends on what you tweet at me, but still. Most of the work presented is not my own only. It's been done with Chris Krugel at UCSB, with Paolo Milani Comparetti, who's now a senior engineer at Lastline, used to be a PhD student in Vienna when we did work together. Engin Kirda, who is now a professor at Northeastern University in Boston. Martina Lindorfer was recently left the Technical University of Vienna. And people from Politecnico di Milano, Alessandro Di Federico, Mario Polino, Andrea Scorti, who is now working somewhere in Dubai, Guido Salvaneschi, who's now at Darmstadt, and Federico Maggi, who's now with Trend Micro. Of course, if all over this, and Mario is shortly going to be a former Polyme student because I'm going to hand him over is very much well-earned doctorate soon. So I'm, of course, there's good things in here, it's their work. There's errors in here, it's my fault. And there's an XKCD cartoon here that I really like. There's pulling a lever, getting a zot. Then the normal person says, whoops, maybe I should not do that again. And instead the scientist says, let's see if it happens every time. And that's me. Questions? Sir, come vuoi? Puoi farla in italiano e poi la ripeto in inglese.
Come, nel caso in cui venga gestita questa circostanza, come il sistema di estrazione gestisce offuscamento basato ad esempio su LLVM, dove ha una rappresentazione assembly completamente diversa ma funzionalmente equivalente.
So the question is about obfuscation, in particular about LLVM. The real answer is we don't. That's not the focus of our research. Actually, if you have I don't know if you have seen it at Black Hat, but in Vegas, a couple of my students presented a very generic unpacker extractor that is actually the prepended to this system, but it doesn't deal with what you were describing. So we are. Yeah, precisely. But yeah, and the same thing happens, for instance, if you have malware that uses, what was the name? Rotalum, I think. The thing where you basically were designing a different virtual machine and writing the code in a different assembly. That's also, I mean, those extreme tricks we don't deal, because that's not the business of this specific system. But that's kind of a limitation, because if we are not able to get to an x86, in this case, representation, we cannot really do this work through. The other limitation, which is major in this work, is that this is obviously meant, as it is right now, it's meant for Windows. Because that's where the majority of malware is, with the possible exception of Android, for which we have another whole line of research that is completely separated. But there's no reason why this should be, in theory, limited to Windows. The only major conceptual issue is what you define as behavior on the other platform. Here it's collections of API calls. Maybe on Unix it would be collections of system calls, or maybe not. We would need to test it, and I cannot say it is. But conceptually, I know, but in theory, but unless I build it and I test it, I cannot. Okay, perfect, awesome. Other questions? Whoa. Okay, I hope it was because I was clear, not because I was completely unintelligible. But thank you very much, and if you have any other questions that pops up, you will find me near the beer stand.